Okay, I'd like to welcome everybody to today's meeting of the CUNY online set theory seminar, and it's my great pleasure to introduce to you Professor Adrian Mathias of Université de la Réunion, and he will give the second in his series of lectures on linking descriptive set theory to symbolic dynamics. Okay, Adrian, take it away.
Thank you. Right. Now, today I'm going to, there'll be two themes. I thought I'd start by giving some ideas about uniform attack. And I have a definition to propose. And a lot of what I say was inspired by Andreas Blass's paper on ultrafilters, where dynamics equals two other things. And he's corresponded with me, and I see he's not certain how much of that paper is his, or he was also surveying past writers. So we'll have to do some checking on who thought of what, but we won't do that during the talk. Now let's see. That, yes. So there's a slight shift. I'll repeat something of what I said. Here I'm looking at a Hausdorff space and a continuous function from x to x. And these, I'm going to emphasize the use of ultrafilters here, which I didn't say much about last week. The t orbit and omega sub t of x is the derived set of the closure of the t orbit. And it's a very popular concept with dynamics people. My first idea, I heard about these problems when I was in Barcelona. I went to a party which was full of symbolic dynamicists. And one of them told me they were using ordinals, and I discovered they didn't actually know that 1 plus omega is not equal to omega plus 1. So their proofs were not very good, but I sorted that out for them and suggested, instead of looking at omega sub t of x, think of the binary relation x attacks y, which is equivalent to saying that y is in the omega limit set of x. But this relation is, if the space is favorable, it's G delta, so therefore Borel, and you can use descriptive set theory, the Kuhn-Martin theorem, but the rank of a Borel well-founded relation is countable. That gave me a big help. And then this lemma I proved, or stated last week, if x attacks A, then x attacks T of A, and T of x attacks A, and it's easy proof there. And if I've got an open neighborhood of T of A, it's inverse open neighborhood of A, so it's arbitrary large things. So Tn plus 1 is of x is in G for arbitrary large n. So that doesn't make any difference to that set of n's being infinite. And now, just to remind how ultrafilters get in here, if x attacks y, define this set A, T, X, G to be, and G is an open set, a set such as, set of n such as T to the n of x is in G. That's infinite if x attacks y. And all the A sub G's generate a filter, which you could extend to a non-principal ultrafilter if you're happy using Zorn. And if U contained both these, ultrafilter U contained both these filters, X is Hausdorff, so you could separate the 2 points B and C by disjoint open sets, and they can't both be in U, so B has to be equal to C. So if X attacks Y, any ultrafilter extending this filter there, the U limit is at most 1 point. So I write T upper U. Here I'm following Andreas's notation. T upper U of A converges if you contains FAB for a necessarily unique B, and then set TUA equals B. So if the limits of the images of X actually converge to Y, F will only contain cofinite sets. If, countable base of neighborhoods, this will be analytic sets and not filter. Sorry. So therefore, in terms of ultrafilters, the omega limit set of little a, a set of Y is such that there's a non-principal ultrafilter with TV of A converging equals Y. And there's a converse. So I've adapted the proof from Andreas's paper showing that X attacks Y if and only if T upper U of X attacks, converges equals Y for some free ultrafilter U, free meaning non-principal. Now, last week I mentioned I was trying to think uniform recurrence. So recurrent point attacks itself. Uniform recurrence, much discussed. So I was wondering, well, a few months ago, how to define uniform attack. And this is my suggestion, say X uniformly attacks Y via the function T if a set of, for every open neighborhood, a set of n such that T to the n of X is in G is syndetic, meaning bounded gaps. There's some m such, starting anywhere within m steps, you will hit this set. Now, for this, we now have to assume the space is regular. I see that various authorities disagree as to what regular means, whether it includes Hausdorff, but regular plus Hausdorff, that seems to be, according to T3. So that's where I am. And David Fremen sent me a message with suggestions for constructing really weird spaces, but I'll mention those later, but I'm not trying to be deliberately weird. And then this is a familiar lemma from point set topology. Which I think probably familiar. And then again, this imitates arguments in Andreas's paper. This, if TVX converges, then for some U, TU of TV of X hits the Y. So you can get from X to Y. So I think the proof is straightforward. And the notation, I think Andreas used M hat for the principal ultrafilter generated by M. And if there's no such M, you can find using the lemma. So there's an N. You can find a big M such that for all n there's a K, T to the n plus K of X is H. So some K works for almost all n, almost all meaning for the ultrafilter V, and fix such a K, then for almost all n, for V many n, that happens. So I can modify my T, take the pre-image using TK times, that we closed, and then there we are. So you're bound to get into any one of these sets, YG, and if you keep shrinking G, then you see each of them are infinite, and they generate a filter extend to an ultrafilter, and you've got what you wanted. And here, easy remark. This is if, in this case, it's periodic, and this lemma imitates the lemma I had for just plain attack without uniformity, but a similar proof works. And now, Andreas in his paper was keen to use compactness. In my papers, compactness wasn't so important, but I did need in certain places metrizability. So I'm really trying to see how far can we get. Now, I don't really know what uniform spaces are, so the ocean of my ignorance surrounds me. So maybe something like that you can get at more than compact metrizable spaces for things to work. So call X T benign if TVX converges for every ultrafilter in V to N V. So in a compact space, compact regular, it will be, every point will be like that. And if this condition holds, so if X is T benign, this converges for every V. And if for every V I can find a U like that, then I've got uniform attack. And again, this is similar to proofs in Andreas's paper. There's a remark about diagonal, and it's useful to be able to define it. Depends how well you know your Stone spaces. U plus V for sum of two ultrafilters. This is set theoretic definition. Andreas gives several others from different points of view, and U plus V has this property. And using that, if you take U to be an ultrafilter generated by a principal ultrafilter, then you can use that in proving this exercise, which I leave to the readers. And now proximal pairs. So you can see it's a similar definition, but you're looking at pairs that, but the U limit of Tnx, Tny is the same as that pair. So if either side is defined, so is the other, and they're equal. I'm using the Kleene meaning for that. And X and Y are proximal if you can get U with Tux, Ty both defined and equal. And it's if and only if. I think there's a converse argument there. And now syndetically proximal, it's similar definition, but you require these sets of successes to be syndetic. And roaming on the web. Sorry?
Could you just say again what syndetic means? And then
there's a
bounded gaps, I think.
Bounded gaps, yes. So wherever you, given any integer, there's an M for the syndetic set, such that you hit it within M steps. The M is
right. And then what is uniformly attacking mean?
Well, I had that up here. This was there.
Yeah, that involves syndetic. Okay, that's
that involves syndetic. Yes, I just found that coming across, people are thinking about syndetic things. Particularly, I was asked to a meeting in Lyon organized by Imre Lieder, where syndetic sets are much talked about. So I thought, let's have a go with those.
You mean like inorganic theory or things like that? Or?
That's it. Yes.
Yeah.
So. I've done that one. That's right. Tu of tvx is tu plus v. That's very useful. And I had this proposition and its converse, and now we come to syndetically proximal, which I found roaming the web. came across a paper which I put in the reference list for last week, synthetically proximal. So I wrote to Professor Musasu, and he answered and suggested I should get in touch with a Polish mathematician, Piotr Oprocha. And these three people found a mistake in the paper by Musasu that I mentioned last week, the counterexample theorem 9. But these other references, there's some nice, I just found Sabina Koppelberg's, I think their notes for a lecture course, but a good read. There are many things, I can't list everything that I ought to have read by now. So here we're using that thing. If X and Y is synthetically proximal, then if I can find a V that both those exist, though possibly not equal, I can make them equal after applying TU. So TU plus V is the same as TU of TV in composition in that order. So I think one of the things I don't know is whether, are there, other than compact spaces, are there spaces with lots of benign points? There's a challenge. But this ultrafilter characterization works as well for benign things. And if it's not proxy Y, then for no M is they equal, so you can find an open neighborhood of diagonal, which gets missed, and is therefore infinite because you can keep shrinking the neighborhood. And as you increase M, these are nested, so a generator, a free filter, so pick a V, and then you've got these. So it's simple analysis going on once you've got used to using ultrafilters and associated maps. Then the lemma is just a straight application of that equation I had. And now odds start to prove things, and they seem to me to be very odd. I hope I haven't made a mistake, but of course it's open to anybody to find one. But if A attacks B uniformly and B attacks C, then A attacks C uniformly. And using these characterizations I've given, well, it's not clear to me that you actually get very much without assuming the space to be compact, but I still have hopes of something happening. So here, if X uniformly attacks B and X attacks A, then A uniformly attacks B, because images of A stay predictably close to images of X, and those get near to B, so the images of A get near to B. That's so I use uniform continuity, yeah. And if I, for every L, there's an I, there's an M such that for every L, there's an I such that those are within half epsilon. And then it's like undergraduate analysis. I can find something with these two, what's using up the other half epsilon, so then I get that. So we get I find these results strange, but I'd be delighted if somebody could check my arguments. And then a weaker form in bare space, which I did talk about a lot about last week, space of infinite sequences of natural numbers, which is, there's a metric, but it's not compact, for the shift function S, which I think I define it again somewhere. You take an infinite sequence, throw away the first term, and then move all the other terms up one. So if X, the great advantage of a shift function is you can actually see what's happening, unlike sort of more vague continuous functions. So here I show if X uniformly attacks B for the shift function and A as well, then these two are shift recurrent. So there's a sort of limit. Things that are uniformly attacked are close to each other in some sense, which is gradually developing. And here we are. Now I have to go back to compactness, because again, I use uniform continuity, similar argument. Don't think it's exactly the same as something I've said before. And we have this, another adapted from that, find the closed neighborhood. So a very similar structured argument to ones we've seen. And in the other way, so I prove it by contraposition. If that fails, then I
So
will.
could I ask, the word uniform came up twice, and I suspect that it's important that like uniform implies uniform. So on the one hand, you've got your definition of uniform that involves syndectic, which is about bounded gaps in integer sequences, and I have a picture of that. And then secondly, in talking specifically about the bare space, which is sort of metrizable in a reasonably standard way. You take some of right uniform continuity. So are you based? I mean, is this somehow the motivation for the use of the word? I mean, because it allows you to sort of jump from the one to the other.
I think my ignorance is going to stop me answering your question. Uniform continuity I've got in metric spaces, and I'm vaguely wondering how does it relate to this other notion of uniformity. Oh,
I thought you said it did. Oh, okay. I'm sorry. I misheard you altogether. We're wondering about the same thing. Okay, go on.
Right. So that's a similar question for all I'm listening to. I can do that. So this is using the uniform continuity, and then I can get two of them close together, and there we're.
Okay, here, could you go back and just point to that when you're saying this is using the uniform continuity, but you do mean the standard metric or a standard metric on the bare space, right?
I think so, yes.
Okay.
Nothing kinky, no.
Yeah, right. I mean, I guess, yeah. I mean, I think probably all those give you the same uniform structure. So
in my talk last week, I had an important section which I called putting points at the end of a path.
Yes.
And that very much used the metrizability of the space, because I said I was looking at a sequence of attacks and then said you could replace the function by at each point by any finite power of itself. Different finite powers at different places, and you could choose which powers you take to get the result to be a koshi sequence. And I don't see how to prove that without a metric, but it might be some,
that's exactly as far as I got just before that, reading the notes.
So that's where ideas are eagerly wanted. So here I show that the hypothesis fails if there's an open neighborhood of Y for which that statement fails. So David Fremlin, I haven't checked yet whether he's happy for me to pass this on to everybody, so I must do that. But an very interesting idea. So take the punctured disk in the complex plane, and then you can put, he's looking at a function which pushes Z out to the edge point. And the question is, when it gets, is there a point? So is there a point on the, start from the interior, and then you're going to add points at certain places. I think this is how, with examples like this is where almost disjoint families got popular with point set topologists. So you can, by choosing which are going to be the fortunate points on the angles, where there'll be a point on the boundary, get different spaces. And some spaces, I rather suspect that what Fremlin's remark can be used to refute some of the conjectures I make later on. I am.
So that's meant to be a metrizable space, or no, or what's the claim here? I'm going to think about the space here. What?
I'm trying to see if there's a space where every point is benign and something nice happens. And
but which is not compact or something like that.
Something like that, yes. But I am rather out of my depth here, because people like Fremlin know infinitely more about point set topology than I do. But there we are. Right. So no more now about uniform attacks. I want to go back. Last week, I started talking about my construction of a point of score omega-1 in Baire space, a recursive point. And as I said, I felt rather like Lachlan did when he completed his paper on O triple jump priority arguments. And he said it was the result of 10 false proofs, and he couldn't face trying to simplifying it anymore. That's how I feel about my proof. But then in Lachlan's case, Leo Harrington in 1982 at the Cornell Summer School presented a clever proof using trees. And I had a copy of his talk and gave it to my Cambridge student, David Ceterpan, who told me it took him 2 years to understand Leo's notes, but eventually, as recursion theorists know, Ceterpan was able to prove very strong theorems using O triple jump arguments. So what I hope, preparing this talk has made me feel perhaps there is another simplification possible for my construction. I'd be delighted if somebody else would find it, because I thought I'm a bit exhausted in this area. But there we are. So I'll repeat a few slides from last week. So I'm in Baire space with the shift function, and I want to code finite sequences, and it was Christian Delamay who gave me this way. It achieved quite a simplification of the proof I had so far. I want to code finite trees, and his suggestion was use sequences like this. They're defined from 1 up to the length of u, not for 0. And u of I is always less than I, some integer less than I, but non-negative. And u sub less than equal to k is the first k elements in the sequence. So since last week, I thought it would be good to call curly f a set of finite Delamay codes. And we're going to see that we use a code, a Delaware code, to code a finite tree, which we think of it as starting at the top and going down and branching. And these trees are going to grow, and the question is whether they grow into a well-founded infinite tree or not. So they may well not be finitely branching. So you might get a tree where it's just got lots of points just below the top, but nothing further down. Now, a U sequence is a sequence taken from the tree that's being coded. So it'll form a path in the tree. So U of pi plus 1 equals pi. I'll give you an illustration in a minute. So the U sequences are the positive U sequences. That's non-empty, and the empty sequence, which I've taken to using the scrambled egg to indicate. And we interpret S less than equal to 0 as the empty sequence. So here's an example. Here's a finite Delorme code. So think of this, its domain is 1, 2, 3, 4, 5. So the value at 1 is 0, at 2 is 0, at 3 is 2, at 4 is 0, is 1, at 5 is 0. So we read this as coding this tree, 0 at the top, 1, 2, and 5 immediately below 0, 4 goes to 1, 3 goes to 2. So that is the little tree that's being coded by this sequence. And the U sequences, the empty sequence, start always at the top and follow a path down. So it might be nothing there, the empty sequence, then 1 or 2 or 5 or 1, 4 or 2, 3. So I gave, well, more examples. And now to remind you how I'm going to build a point in a space of infinite sequences of countably many symbols. But symbols are not going to be natural numbers. They're going to be codes of things which give information about what the tree is going to do or has just done. So I said I call the 3 kinds of symbols: recorders, predictors, and markers. And so to think of a symbol as a little button on which something has been written. And so we sequences of those. And so the recorders will just have an element of Delorme code written on it. Or there'll be a pair of sequences where U is a Delorme code and S is a positive U sequence, so a path through U. And those are going to be called predictors because they contain information about what's going to happen next. And the markers, they just have to be different from all the recorders and predictors and different from each other. So it's very important that each symbol is a single object, and that's why I use square brackets. The symbol will be square brackets, and then what's written on the little bean is what's inside the square brackets. And if I want to name a finite or infinite sequence of symbols, I will use pointed brackets at the start and the end. In each recorder and each predictor, I define the weight and the height. So, definition not yet. Recorder is an object like that. Its weight is 0, and its height is the length of U as a Delorme code, remember that. Predictor is SU, where U is a code of a tree and S is a code of a non-zero path through that tree, not necessarily getting to an endpoint. Just the path, as I showed you, the paths could stop, and that's important. Predictor's weight is the length of its path, and its height is the length of its tree. And then, of course, the weight of S can't be greater than the height. But it might be that a sequence, the largest natural number in S is the same as the length of U, in which case we say U tightly contains S. Otherwise, we'll say it's loose. And looseness of U over S is the length of U minus the greatest thing in S. So then I'm going to define for each U and S, each Delorme code and each path sequence in that code, I define this finite sequence. And the definition is what I call, by a process I call double induction. First, consider the case S is the empty sequence. And then, having made the definitions in that case, we suppose M is at least 1. So S, we have already treated all pairs with a U sequence of length less than M. So then take an S of length M and consider all those U for which S is a U sequence, starting with the U which is tightly contains S, and then progressively treating along the U. So we're proceeding by induction of the looseness of U over S. And this, last week I was ticked off by saying prime instead of dash. S primed for sequence with its last element removed, with the largest, and U primed with its last element removed. And now this is the definition, this is the crucial thing. So ZU empty sequence is, I just have a sequence of recorders getting longer and longer, all of them are initial segments of U. So with that one, the example I'm working with, it looks like this, 0, 0, 0, 0, 2, 0, 2, 1, 0, 2, 1, 0. And the length of that equals the length of U. So that's easy enough. And now, to define ZUS. So it might be that S is tight in U, in which case this sequence is this predictor, and then the sequence ZUS dash, whatever that is. So I've shortened S, taken away that, so that's already defined. And if the maximum of S is less than length of U, I begin with that, so I knock something off U. That S is still a U primed path because of this condition. Then that predictor and then that sequence. And this predictor only occurs once in ZUS because it's the only one, it's the only symbol with sum of weight and height equal to that sum of the length of S and sum of the two weights. Now, last week I gave thousands of examples. I won't repeat them, but I'll do just the easiest one. So, if we've seen what ZU empty sequence is. Sequence, this is tight 5, so that looks like that. Sequence of symbols. Well, ZU2 turns out to be this, so it's 18. All I can just do is take my definition and check that I've got it right. So an M predictor is a predictor of weight exactly M. And as I'm using the shift function, will be an M stretch is a finite sequence of symbols, all of weight at most M. So if I'm looking at a finite or infinite sequence of symbols, a stretch is a an interval, convex interval there of each of the m members at most m. So if S has weight bigger than m, then I can, and if X is a stretch, an M stretch in ZUS, I can knock off the last thing of element of S, and I can go on knocking off top points of S until I get down to an S of weight exactly M, and then X will be all right then. Well, that's the proof I've just given you. And this, I hope you can now believe that if X is an M stretch and as in of ZUS, I can shorten both U and S. That's it there. So recorder coherence means if you look at them as just sequences, one is initial segment of the other. And then I gave this proposition last week. It's highly important. If the same symbol of weight M occurs twice in one of these sequences, then between the two occurrences, there must be an occurrence of a symbol of weight M plus 1. And the proof, the indicated symbol, which occurs twice, it can't be the peak of ZUS because the peak only occurs once. If S is tight, then from the definition, both the occurrences are in ZUS primed. And now we've reduced to an earlier case because we've got S, we've shortened S. Otherwise, ZUS looks like this, ZU primed S, the predictor ZUS primed. And if both the occurrences of the symbol I've got my eye on are here, we've reduced to an earlier case. If they're both here, we've reduced to the earlier case. Or one is here and one is there. But then the peak is of weight bigger than either. So if it's of weight more than M plus 1, I had a lemma saying that the next few symbols, it'll come down, declining by 1 at each step. So I'll get to a point of weight exactly M plus 1 before there's a chance of that symbol recurring. Now, infinite sequences, I think I did give this symbols. Y, curly Y is the space of all sequences of length only of symbols, and they can be either recorders, predictors, or markers. And now the shift function is defined as usual. The shift function applied to the sequence zeta. Its value at n is zeta of n plus 1. So you've thrown away what zeta of naught was. You don't know that anymore. And I say zeta is near to psi if when I remove some finite initial segment of psi, I've got zeta. And now I define for infinite these sequences. The weight is supremum of the weight of its predictors, and the height, the supremum of the height of its recorders and predictors. Now, then the point I've promised, the recursive point B, which will lie in the space Y. So I enumerate all sequences ZUS in some recursive fashion, and then I just list them all, separating each by, that concatenation has gone up a bit too high. Probably that didn't like that bracket, it's a pointed bracket. Separated by markers. And the theorem is that the score of this point B is actually omega 1. So to prove that, we have to, we've looked at finite Delamay codes, and I want now to look at infinite Delaunay codes. So I define curly T, so it's infinitely long things, but satisfying the condition that finite Delaunay codes satisfy. And so this is it.
That's actual omega-1 or Church Cluny omega-1?
No, actual omega-1.
All right, so wait a minute. I thought early on, I thought it was established for very general reasons that things have to be countable. So what am I missing here?
What I showed last week was that you've got a shrinking sequence of sets repeatedly using the, and each point which disappears from the original set disappears at a countable stage.
Yes.
But this point B, I'm going to show that for any countable ordinal, there will be something attacked by B which lasts that long before it's chucked out.
Okay.
So the score being how long it takes before you no longer lose things for this B is omega-1.
Okay.
Now then, T is a set of infinite Delaunay codes. Yes. So it's actually a compact space, so I don't know how to benefit from that, but because at each point, there's only finding any choice of values for tau. And a tau sequence, positive tau sequence, it's the definition as before, except that you allow infinite sequences, which I now call a tau path. And given the tau path, I can look at finite initial segments of it like that, as I did before. And then everybody knows about well-founded and ill-founded trees. And every accountably infinite tree, I shouldn't have used that T perhaps, but of finite sequences under end extension is coded by, well, you can code any accountably infinite tree by some tau. It's not difficult. The problem is that it might be infinitely branching. So the way you assign numbers, you do it first without worrying about which order you choose integers, and then revise it. But the proof is in the paper. And now you start looking at properties of infinite sequences attacked by B. And all these lemmas and propositions go back to things we've already shown about finite things. So it's just a question of checking back the definitions that they work. I've had a bad week because I had a horrible shock to find I have difficulty understanding my brilliant paper of 20 years ago, but I'm hoping that I shall do so sooner or later. So any two recorders in Xi, if Xi is a point attacked by that, if B attacks Xi, Xi can't contain any markers because each marker only occurs once in B, so it have to occur repeatedly there. So each segment of Xi, initial segment of Xi is a stretch in ZUS and UNS. And then using my lemmas, if B attacks zeta and there's an M predictor in zeta, they'll occur infinitely often. And in fact, so there should be a shift sign there, but I left it out. If B attacks zeta, the height is infinity. So it depends on its weight, which and if it's of infinite weight, then it must be of infinite height. So it contains recorders. So if B attacks these, it has recorders of unbounded height. And they you can read back from zeta a member of T, a Delaunay code that are called T zeta, and only initial segments of T zeta will occur in zeta. The question is whether zeta has infinite weight or not. And so you first look at points of finite weight attacked by B. So given an infinite code, I can look at these unions of things that's going to be an element of symbol space Y. So if there are no predictors in Xi, or this, if an S is the empty sequence, you just get infinite sequence of recorders like that. And then, I don't know if that helps you to meditate on that, but if the maximum, if S is positive tau sequence with maximum element 5, then you get all these so that the path stays fixed in length, but the rest gets longer and longer. So, and this psi TS, you could get tau back from it. So now look at points of weight naught attacked by B. It attacks each of these. Nothing near that attacks itself. Well, as I say, you have to check all the lemmas, but I think that I feel like Boris Johnson telling you that everything's under control. Phi attacks zeta, then zeta's near to one of these, and we'll know how many shifts to take, because it will be the height of zeta naught. And something much the same happens for finite weight. And if the weight is bounded, then you're going to have infinitely many predictors of weight m, but essentially nothing further. So you'll be able to work out, find a T zeta and an S T zeta. I have to find an S zeta of weight m, maximum weight in it, and zeta will be near to that. And now if S is one shorter than T, then T psi tau T attacks psi tau S. And if you read my first paper on this, this is how I built up embedding arbitrary, well-founded, countable, well-founded trees into the attack relation shift. It's the same idea there. So that iterated gives you that. And now we want to look at points of infinite weight, where that thing is so the union of the trees of the predictors in zeta, they go arbitrary large weight, gives me a tree. Union of the paths will be of the predictors. The path in the predictors is a finite thing, but if it's zetas of infinite weight, these paths grow to an infinite path, which I call T zeta, a path I call pi zeta, and that makes sure T tau zeta is ill-founded. And now this is where that thing about points at the end of paths that I talked about comes in. And this is where the koshi sequence argument, well-chosen finite shifts, and that zeta attacks that. So this is really the argument that I had last week in this particular context. C.C. Chang said once that it was amazing how much Ronald Jensen proved, given that there were never any ideas in his proofs. And this is a Jensen style thing. All the ideas are in the definitions, and once you've mastered those, the proofs are easy. So therefore, if B attacks zeta of infinite weight, then there's a zeta is recurrent, and it's at the end of a tau zeta path. So all points of infinite weight attacked by B are recurrent, and the converse is true. And this is where we use effective. If it has no markers, so every initial segment is a stretch of some ZUS. So it will have to contain recorders. So any, as well as recurrent, any symbol in it recurs infinitely often. And between two occurrences of the same recorder, there must occur predictive weight 1. Between two occurrences of the same predictive weight 1 must be weight 2, so on. As that shows this characterization. Rho is recurrent if and only if it's of infinite weight. And I've got an illustration here. Possible ways to which recurrent points can arise. This, I didn't understand my tech because I had this perfect, and then suddenly this morning, this diagram, the tech complained, and it turned it was I did have corrected it now. I don't know why I did that. I think my laptop was getting tired. And it suggests other ways of constructing recurrent points. And now we want to show those points of finite weight with arbitrary large score, countable score. So this is where the way I'm using the alphabet generated by markers and predictors and recorders is to get different paths to not attack each other. So if B attacks psi and tau psi is not the same as sigma, then psi sigma s is not attacked by psi. So if zeta is attacked and this sigma is well founded, if this zeta has to be a finite weight. Sorry. So what are near to these? This is where the action is. And now if sigma is well founded, the point psi sigma empty set, the point where it isn't attacked initially, but leaves the shrinking sequence of the omega sequence that I had at the beginning, attacked by B and the shift function. The moment it leaves is the rank of the tree it's coding. So it's really just as in delays. I showed how in delays I was doing this just one tree at a time, so I didn't have to worry about having uncountably many trees to think about. But it's essentially the same idea. And then I've really said everything needed. I've shown there's arbitrary large theta score of B is larger than any countable ordinal. I've showed in delays it couldn't be bigger than omega-1, so it is exactly omega-1. So we have this nice picture. The recurrent points attacked by B are all at the ends of paths through ill-founded trees and all maximal recurrent in the sense I discussed last week. Maximal recurrence is, I think, maybe my discovery, but I can't get the dynamics people to be interested in it for some reason. And the points of escape are those near to these. So the point of escapes, after finitely many shifts, it is exactly one of these. And then you got a very good account of how those. So the abode, the points that are not chucked out, is complete because we've got a continuous reduction. We can test ill-foundedness by knowing which is in the abode. And so the escape set is a complete co-analytic set. And I'll just mention in the last few minutes, Martin Goldstone asked if the set of alpha in bare space with the omega limit set countable, whether that was a complete co-analytic set. It's co-analytic because by perspective, if Harrison's theorem, isn't it? If that's countable, it makes beta hype. Yeah. Alpha attacks beta. Beta would be here, and countable. All the members of a pi1 set with no perfect subset are hype in the code. So then I just repeat my proof to say that I can exhibit a continuous reduction of a collection of well-founded trees to this set G. So it's just examining my proof. I slightly change the way I've done it, but then you get all that. So another proof, and now some open problems. These I mentioned last week, but I've added some more. This is Cummings' score pi1 norm. I don't know. But I thought you might have to look at functions where there's no point of uncountable score, just because in a lot of cases there isn't a point like that. And then that might be a pi1 norm in the sense of descriptive set theory, Kekris and Moskowakis, I think. Possible scores of recursive members. This problem was last week, but I've told you this today, my suggestion for a definition of that. And I just wonder how much use it will be. And then this, the Outlander-Ellis theorem is, it's in this neighborhood. And I just wondered whether there are many proofs of it now known, but I'm just wondering whether these ideas might give another proof. Locked is a short paper I wrote, choosing an attacker by a local derivation. But it gives a procedure for picking ones, and there were some good problems in that paper. You have to look at the paper for the definitions of these things. Now, putting points at the end of paths would work without a metric. I don't know, because my proof very much used the koshi sequence argument, and I had no ideas for that. If X is uniformly recurrent, will that converge for all V? And if X is benign, is T nu V of X benign? Which this, if TV was onto everything, then you might be lucky. But as I said, the sketches sent by Fremen for building strange spaces might show these answers are negative. So,
Good night, Adrian.
Right.
There was a lot of information in these two talks.
You were what?
There was a lot of information in these two talks.
Oh, yes, I'm sorry. Yes. Still. Now, does anybody want to ask me a question?
Questions for Adrian?
I have a comment.
Yes.
It's a little risky because it involves trying to remember what I was thinking about 30 years ago when I wrote that paper.
Yeah.
I think in the background of that paper, there were considerations involving uniform spaces, which may help here as well. The point is that there are these two worlds. There's the metric space world, where most dynamical systems people and a lot of other mathematicians live. And then there's the compact world where ultrafilters converge and everything else is nice. Right? And the main point here is that uniform spaces connect the two in the sense that a metric on a space induces a uniform structure, and a compact Hausdorff space has exactly one uniform structure inducing that topology. And so one can sort of take concepts that were stated for metric spaces, like the notion of proximal points, proximal pairs of points. The definition visibly generalizes to uniform spaces, and then interpret that uniform definition in the compact world. And that, if I remember correctly, is the source of like proximal being images of the pair in every neighborhood of the diagonal, which doesn't sound like it's using uniform structures, but that is the definition of the uniform structure on a compact space. It's the neighborhood of the diagonal. So I suspect that a lot of the compact stuff was done by pushing over via uniformities what people were accustomed to in the metric world, and then say, hey, look, ultrafilters work beautifully in these compact spaces, so let's work with that. In particular, I'm not entirely convinced that defining proximal in terms of neighborhoods of the diagonal is the right way to go in the metric space context. It may very well be that you want proximal to mean what metric people mean, which I think means that given any epsilon, if you iterate enough, this pair of points gets within epsilon of each other.
Yeah.
So there may be some definitional issues that deserve some uniform space attention.
Thank you very much. It's, so I really got to find out what a uniform space is, which escaped me in my undergraduate days.